In this part of Chapter 3, Deformation and Strain, we are going to study the deformation gradient and a few measures of strain or a few measures of deformation. These measures of deformation are what tell me whether a material exhibits strain or not. And we're going to start by recalling how to describe a set in R3, a line in R3. If you recall from the beginning of the previous lecture, a smooth line in R3 can be described by a one parameter family of vectors. So I have a parameter xc that describes the length along this line, and I have a family of vectors, capital X, that for each xc I have a vector x. For each xc I have another vector x. For the beginning of the curve I have an initial vector, and for the end of the curve I have another vector. Now let's apply this to a continuum. If I have a continuum in the deformed configuration, in the reference configuration, and is described or represented by omega naught, every point is represented by a vector in the set omega naught. So the set omega naught represents the reference configuration of the object. After deformation, this object is deformed such that the new vector representation is small x, and the object is represented by the set omega of the deformed configuration. If I draw a line, a material curve, on the reference configuration, I can say that this line is described by a one parameter family of vectors. Xc is equal to xc1 as a function of x is equal to x1 function of xc in the direction of e1 plus x2 function of xc in the direction of e2 plus x3 function of xc in the direction of E3. So you give me a value of xc and I tell you the position of the point along this line by giving you the different coordinates of the point x1, x2, x3, all functions of the variable xc. Now, if the deformation is described by the function f that maps every point in the reference to configuration to another point in the deformed configuration, then the new position vector of that family of vectors is described by x, where x is equal to the first component, which is a function of both the x and of course time, because things could be moving in time as well, plus x2 as a function of x, which is a function of xc and time, plus x3 as a function of x and time. Now what we're usually interested in is local deformations. By local deformations, I'm interested in what happens to tangents to this line. So if I draw a tangent here to this line, and I call this tangent n, I'm interested to know what happened to this tangent, because in this tangent I will know whether locally after deformation, the material has increased in length, decreased in length, or stayed the same. So this vector n, which is the tangent, can be obtained using the following formula. By taking the derivative of the position vector with respect to xe, I can get the position vector. Sorry, the tangent vector. So n is the tangent vector in the reference configuration. The small n, which is partial x by partial xe, gives me the tangent at the same point in the deformed configuration. Now I'm interested in how the small n relates to capital N. So n is equal to partial x by partial xe. I can this is equal to partial x by partial capital X multiplied by partial x capital X by partial xe, which in component form takes the following form. So n, which is equal to partial x1 by partial xe, partial x2 partial xe, partial x3 by partial xe, we know that x1 is function of 3 components. So I can take partial x1 by partial capital X1 multiplied by partial capital X1 by partial xe, partial x1 by partial x2 multiplied by partial capital X2 partial xe, plus partial x1 by partial x3 multiplied by partial x3 by partial xe, and so on. If we take these components out, you can form the following matrix. This is equal to partial x1 by partial capital X1, partial x1 by partial capital X2, partial x1 by partial capital X3, and so on. If you take those small components out, and if you call this matrix F, and this vector is actually n because this is the tangent vector in the original in the reference configuration, you get this relationship between the tangent vectors in the deformed configuration n and the tangent vectors in the reference configuration capital N. They're both related with a matrix F, and this matrix is called the deformation gradient because it has the gradient of the position function. Its components, the components of F, are the gradients of the small x with respect to capital X. Now, inside this matrix, I have all the information that I need regarding local deformations. So basically, if I have an object and I draw a small tangent curve on that object, after deformation, let's say this object takes the shape, and now this tangent vector becomes this small tangent vector n that is related to the original vector by the matrix F, and F is the deformation gradient that relates small x's with the capital X's. So let's try to understand what the properties of this matrix are. First, this deformation gradient contains the information on the local volume changes. So if I have an object here before deformation, and I have three tangent vectors, n, m, and p, and these tangent vectors give me a small cube of material, and the volume is equal to p dot m cross n. So p and n and m are three material vectors at a point. The local volume is equal to, inside those three vectors, is given by the triple product of p and m and n. After deformation, if I know the deformation gradient, then these tangent vectors are now fn, fm, and fp, and the new volume is equal to fn dot, or the triple product between those three vectors, fp, fm cross fn, and if you recall properties of determinant, of a matrix in R3, the determinant of F gives me the ratio between the volume after deformation and the capital volume before deformation. And so the determinant of F, if I have this matrix F, I can know whether the local change in volume. If I know at this point, if I draw those three vectors and those three vectors in the after deformation, I will know that locally the ratio between the volume at this point and the volume at this point is given by the determinant of F. If an object has its volume not changing as it deforms, for example rubber can have huge shape changes, but the volume does not change. So for isochoric motion, deformation is not accompanied by volume changes. In that case, the determinant of F is equal to 1. Example, if you have a deformation such that F is equal to 1 tan theta 0, 0, 1, 0, and the determinant of F is equal to 1, this deformation is isochoric, and check previous lecture to see what kind of deformation this particular f describes. So there are two types of, we can describe the motion as homogeneous or non-homogeneous. A homogeneous deformation is a deformation where the deformation gradient does not change across the object. For example, I'm going to get an object. This is the reference configuration. And in the deformed configuration, the object extends along E1 such that F, so uniform extension, in a uniform extension we know that x1, let's say, is equal to a function, a multiplier multiplied by x1. Let's say x2 does not change, x3 does not change. In this particular case, x is equal to k1 0 0 0 1 0 0 0 1 multiplied by x1 x2 x3. In this particular case, f is constant or independent of position. So f is called, or the deformation is called, homogeneous. If, on the other hand, I have f as a function of position, f is a function of position inside the object, the deformation is called non-homogeneous. Example, I have this object. After deformation, I have this kind of deformation. You can find that at some locations volume might have changed, in other locations volume might not have changed, so that the deformation is not homogeneous. And if this is a material vector here, maybe it will keep its direction at this spot. If this is a material curve at this point, it will have a different direction, and so this is a non-homogeneous deformation. And you're going to find that f(x) will be a nonlinear function of x. Since it's a nonlinear function, example, x1 squared, x2 squared, x3 squared, then you're going to find that f will be a function of position because it's going to be equal to 2x1, 2x2, 2x3. You'll find the position components are explicitly appear inside F, and so this is a non-homogeneous deformation. Again, a homogeneous deformation is when F is not function of position. For example, here F is not function of position, all the entries of F are constant. In this second case, the entries of F has position inside of them, so it's called a non-homogeneous deformation. Now there are, in general, a matrix can have any 9 values that you input in them. This even if you put all zeros, this is a valid matrix. However, for a matrix to describe a deformation, or for a matrix to be called a deformation gradient, there are some restrictions that come from the physics of the deformation. And these are as follows. If this is n, and this is m, and this is p, 3 vectors in R3 actually, and they are elements of omega naught, Fn, Fm, Fp are elements of the object after deformation, so they're the images of n and m and p after deformation. For the material, or for the deformation to be physically possible, the determinant of F has to be greater than 0. Otherwise, the material will be squished and the volume and the local volume after deformation will be equal to 0. If, on the other hand, so if the determinant of F is 0, then material or object is squished. That's what we just said. Then the object is squished. Now, what if the determinant of F is less than 0? What does determinant of F less than 0 mean? It means the following. That the triple product and M and P, which gives me the volume here, let's say P dot N cross M, if the determinant of F is less than 0, it means the following. If I have 3 vectors n, m, and p, and the local volume before deformation is equal to the triple product between p, n, and m, then after deformation, the orientation of the vectors with respect to each other has changed, because now the volume which is equal to fp dot fn cross fm, you can see that the vectors n and m after deformation switched their orientation with respect to p. So they changed their, whether they were if they're following the right hand rule before deformation, now they're following a left hand rule, or if they were following the left hand rule, now they're following the right hand rule. So in this particular case, the determinant of f is less than 0, which means material has turned inside out. This deformation is not physically possible. And so from this we see that if I have a deformation, to know whether it's physically possible or not, if I already have the position function, I find the determinant of that deformation, or the deformation gradient, the determinant of the deformation gradient of that deformation, and that will tell me whether this is physically possible or not. Because to be physically possible, the determinant of f has to be greater than 0. Now I'm going to show you a problem, or present a problem that shows you how we can find the deformation gradient given the description of the deformation described by 3 vectors before and after deformation. So if I have a continuum body that deforms such that the vectors dx given by this, and dy given by that, and dz given by this, they all deform by to become dx, which is given by this vector, dy given by this vector, and dz given by that small vector. We need to find the deformation gradient, and we need to know whether this deformation is physically possible or not. So I know that the small dx is actually equal to f capital dx. dy is equal to f capital dy. dz is equal to f capital dz. And I know that f has 9 numbers. And these 9 numbers are what I'm looking for. So I need to form nine equations in 9 unknowns. So the first equation is the component y's, dx1 or dx, which is equal to 1, 0, 0. This equation is equal to f11, f12, f13. These are the numbers that I'm looking for. f21, f22, f23. What are all these numbers? Multiplied by the original dx, which is 1, 0, 0. So this is basically, these are basically 3 equations. 1 is equal to f11 multiplied by 1 plus f12 multiplied by 0 plus f13 multiplied by 0. 0 is equal to f21 multiplied by 1 plus f22 multiplied by 0 plus f23 multiplied by 0, and so on. So these are 3 equations, 1, 2, 3. The third equation is 1, 1, 0, which is equal to, dy 0, 1, 1, small dy 0, 1, 1, again is equal to those 9 components multiplied by the original dy, which is equal to 1, 1, 0. Again, these are 3 equations, 1, 2, 3. And the third equation, dz, which is equal to 0, 0, 0, 1. This this is equal to f, the 9 components, multiplied by the original dz, d capital Z, which is 1, 1, 1. Again, 3 equations. Count the equations 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 unknowns. And you'll find that the determinant of f, you'll be able to find the 9 components of f. So solve 9 equations in 9 unknowns, and I will show you how to do this in Mathematica in a different tutorial. And compare or compute that f. Compute the determinant of f if determinant of f is greater than 0, physically possible. Otherwise, if the determinant of f is less than 0, then the deformation is not physically possible. This next matrix that we are going to present is what we call the displacement gradient tensor. So far we have presented x as a function of x, and we have said that x or f is a matrix that gives me the gradients of the components with respect to, so the deformed components with respect to the original components. And this matrix has information on local changes of volume and local changes of direction. There's another matrix that we can use to also describe the changes in the directions and changes in the lengths of the vectors with deformation. This matrix is called the displacement gradient tensor. And this matrix is described, as the name implies, it's the gradient of the displacement. So if the vector u is given by x minus x, the gradient of u, which is partial u by partial x, which in component form equals to partial u1 by partial x1, partial u1 by partial x2, partial u1 by partial x3, and so on. This is also equal to partial, since u is equal to small x minus capital X with respect to capital X, which is equal to partial small x with respect to partial capital X minus partial capital X with respect to partial capital X. Of course, partial capital X with respect to partial capital X will give me the unit matrix, or the identity matrix, and partial small x by partial x will give me the deformation gradient f, so f minus I, which means that the displacement gradient tensor is equal to the deformation gradient tensor minus I. Or, in component form, you can simply write it as follows. partial x1 by partial capital X1 minus 1. Partial x1 and so on. Partial x3 by partial x1, partial x3 by partial x2, and partial x3 by partial x3 minus 1. So this is also a different form of the displacement gradient, which is partial ui by partial xj. So let's try to understand what this displacement gradient tensor, or why would I use the displacement gradient tensor? In fact, the displacement gradient tensor is used to calculate what we refer to as our strain, our general or our small strain matrix that we use for most linear elasticity problems, is actually calculated from this gradient of displacement tensor. So let's try to understand this displacement gradient tensor. If I have a vector dx, this is a vector in a material vector drawn on my object before deformation. After deformation, this material vector becomes small dx, and small dx, as we said, which is a tangent to the material, is equal to the deformation gradient f multiplied by capital dx. Now, if I draw dx, this is f dx. This vector of deformation, which is equal to small dx minus capital dx, is in fact equal to f capital dx minus dx, which is f minus I capital dx, which is basically equal to the gradient of the displacement tensor multiplied by dx. So basically this matrix gradient of u, which is the displacement gradient tensor, I would call it for short the gradient of u. If I multiply this matrix, remember any matrix, the function of a matrix is to multiply it by a vector, because any matrix is simply a linear map of vectors. So if I take this matrix and multiply it by the original vector dx, it gives me this change in that vector. So it gives me this small vector that I call the gradient of u multiplied by dx, which is basically gives me the local changes of the length and the direction of dx. So this small vector, gradient of u multiplied by dx, I can decompose it into two components. A component that tells me the change in the direction, and the component that gives me the change in length. So gradient of u is a matrix. It's a 3 by 3 matrix. I can take the symmetric part of it and call it the infinitesimal strain tensor. And describe it as half the gradient of u plus the gradient of u transpose. And I can take the skew symmetric part which is equal to half the gradient of u minus the gradient of u transpose. And if you remember from linear algebra, that your elementary linear algebra, the gradient of u, the whole matrix, is made out of two matrices, the symmetric part plus the skew symmetric part. And indeed, if you put half gradient of u plus gradient of u transpose plus half the gradient of u minus the gradient of u transpose, you're going to get the gradient of u again. So the gradient of u can be decomposed into a symmetric component and a skew symmetric component. The skew symmetric component is used to describe the change in length, and the skew the symmetric component tells me the strain in the material, and the skew symmetric component tells me the rotation inside the material. So if I have a small vector dx after deformation, which is equal to the original plus the gradient of u multiplied by dx. Remember, I have a small vector dx after deformation. Originally it was dx, and then this dx changed by the gradient of u multiplied by capital dx. This is equal to dx plus half the gradient of u plus the gradient of u transpose dx plus half the gradient of u plus the gradient of u transpose dx where these are matrices. And so if you look at the figure, small dx is equal to double dx plus a component due to the change of direction plus a component due to the change of length. And so this component is what tells me what the strain inside the material is. Now let's look at the physical interpretation of this epsilon inf. This epsilon, which is the infinitesimal strain tensor, is equal to half gradient of u plus the gradient of u transpose, which is equal to the following. Partial u1 by partial capital x1 half partial u1 by partial x2 plus partial u2 by partial x1 half partial u1 by partial x3 plus partial x3 by partial u3 by partial x1. This is symmetric. Here partial u2 by partial capital x2 half partial u2 by partial x3 plus partial u3 by partial x2. This is symmetric. Partial u1, partial u3 by partial x3. So let's understand what the diagonal components mean and what the off-diagonal components mean. The diagonal components of this matrix give me the engineering, which we will study later, engineering longitudinal strain along E1, along the direction E1, E2, E3. So this gives me the longitudinal strain along E1, this gives me the longitudinal strain along E2, this gives me the longitudinal strain along E3. The off-diagonal components give me the engineering shear strain in the planes E1 and E2, E1 and E3, and E2 and E3. So this gives me, in fact, half. So give me half the engineering shear strain in the planes E1, E2, E1, E3, and E1, E2, E3. So we're going to study this later when we cover cover the different strain measures. Now, before we continue the different strain measures, I will just introduce a concept that I will probably not ask you about in any of your exams, which is the polar decomposition of the deformation gradient. So not covered in the exam. So I can always decompose any matrix with if the determinant of f is greater than 0. I can prove that I can decompose the matrix into two matrices, one describing stretch and another describing rotation. So what does it mean by a decompose a matrix? Let's just give an example of matrix decomposition. If I have a matrix M is equal to 2.5, 0, 0, 0, 2, 0, 0, 0, 4, I can almost see that this is equal to, that M is equal to two matrices multiplied by each other, N multiplied by P, where N is equal to 0 0.5, 0, 0, 0, 0 0.5, 0. While P is equal to 1, 0, 0, 0, 4, 0, 0, 0, 8. In fact, I can find thousands of matrices that when I multiply them by each other, I can get in fact, I can find infinite number of matrices that when I multiply them by each other, I get m. However, if the determinant of f is greater than 0, I can find only two matrices if determinant. I can find two unique matrices. Only two of them this kind. One is symmetric and one is a rotation, such that f is equal to r u, where u is symmetric and r is a rotation. And if you remember what a symmetric matrix describes, it describes stretch, or I can also find another two unique matrices. One is symmetric and one is a rotation, such that f equal v r, where r is a rotation and v is symmetric. And what does this all mean? It means the following. Any matrix F describes the deformation by taking a circle of vectors and giving me a deformed shape of that circle. You can always look at this deformed shape as the decomposition of two operations. In the first case, when F is equal to RU, R is a rotation and U is a stretch, the first operation is U. So I take every vector here and apply a symmetric matrix, and if you remember, a symmetric matrix stretches its two orthogonal eigenvectors. So we take the two orthogonal eigenvectors, one can get longer, the other one can get shorter, or both can get shorter, or both can get longer, but they do not change their direction. So the symmetric part expands or contracts or forms this ellipse by simple stretching. And the rotation matrix then takes the new vectors or the new shape and applies a rotation to every vector. So this is how, and this is unique. So if I have f, there's where the determinant of f is greater than 0, this decomposition is unique. I can only find one u and one r to perform such operation. Or I can represent this with a different decomposition where the rotation is first applied and then the stretch. So basically, if I have a circle of vectors, and this is the circle of vectors after deformation, I can decompose this deformation into two shapes, or into two steps. In the first step, I take this circle and I rotate every vector using a rotation r. So every vector p becomes rp, q becomes rq, and they are rotated by a certain angle. And after a rotation, I take v and I apply a stretch to the new circle where the two vectors that are the eigenvectors of v, these two vectors do not change their direction. They keep their direction, but they change their shape and become by lambda 1 and lambda 2, which are the eigenvalues of v. And so any basically what we're trying to show here is that any deformation is decomposed of two parts. First part is a rotation, and the second part is a stretch. And any deformation, deformation that's described, that's physically possible and described by a determinant of f that's greater than 0, can be decomposed into such deformation. Now we're going to use the different types of measures. We're not going to use the deformation gradient for the rest of this chapter. We're going to use the different strain measures, and we're going to try to understand what the different strain measures are, what their advantages and disadvantages are.